My name is Aryaman Singh, and this is my Physics Lab 5 with Slinky Physics. And so today's purpose is to demonstrate the practical application of physics principles by analyzing the motion of a slinky in the frame of gravity and tension and drag. It seeks to validate the fundamental physics concepts of Newton's second law. And so the foundation is we have a few different equations we need to use. So the net force equation, which is the sum of all forces, then the position update and the velocity update formulas, and then the drag force formula, which is Fd equals pv squared times j hat, and then the gravity formula, which is on the surface of the earth, which is Fg equals negative mg times j hat, and then the tension force, which was just the opposing force of any here. And so a brief preview of our experiment was that we have a model of a slinky falling, and we created an observed model and then also a computational model. And so we'll analyze that now. And we have a calibration stick defined as 4 meters or 4 feet or 1.22 meters. And then the axis starts at the bottom of the slinky, and we're going to watch how it falls relative to the top of the slinky. So in this observational model, we can see that the slinky falls, and we're tracking the position at the bottom of the slinky, as we can see here. So as it falls, we track it, and we measure its displacement. And so right now it's 0, 0, 0. And once the top of the slinky hits the bottom, it falls together until it hits the bottom. So we can track the y on the side right here. This is the graph of the observed model. And then we'll use this as inspiration to build our computational model. And so it spans from 0 seconds to 8.25 seconds. And we've taken that as our basis. And we're assuming that the mass of the slinky is around 0.204 kilograms, which is the average mass of a slinky. And then 4 feet, because average height of a human. Here's our glow script code that we use to model that falling slinky. So we've created a sphere and a plottable graph, and then we're going to define the sphere's initial mass to be 0.24 kilograms, and then we'll take its initial position to be 0, 0, 0, because we're looking at the bottom of the slinky, and we define our coordinate axis to be at the bottom of the slinky. And then we're saying that the slinky velocity initial is also 0. And our initial time will be 0 as well. So I took the number of frames and I put it over under the total time. So that's our delta t. And then our g is 9.8. Our j hat would be vector 0, 1, 0. So it's just the direction of gravity and drag and tension. Since there are no forces acting in the x direction that we care about, we're only focused on the y direction. So our j hat is only 0, 1, 0. And then we have our gravity formula and then the opposing tension formula. Then you have our F net, which is the sum of the forces, and our position update formula right here, based off the net force. And we repeat that before the bottom of the slinky reaches the top of the slinky, before the top of the slinky reaches the bottom of the slinky. Once they hit, then we have drag and gravity acting together instead of tension. We repeat that same net force formula with the drag, and our B is 30, and then our B constant is 30, and then we do the same position update and velocity update. And then we graph it, and it looks like this. There it's falling. If we plot the observed and computational model, we can see somewhat of a difference. It looks like the observed model falls earlier, and in the computational model it falls later. And then also the time it takes for it to fall is much longer in the observed model as opposed to the computed model. So there could be different reasons for this error, but the idea here is that our model is still pretty similar. So we got a general idea of what's occurring in the falling slinky. There's a tension force acting up and a gravity force acting down up until the top of the slinky reaches the bottom of the slinky. Then it's all one object or one mass, and then there's no opposing forces, only besides gravity and drag, and there's no tension really. And so the error could have come from measuring the calibration stick. So it might not be exactly 4 feet. There could be an error in determining the point of mass, an accurate B constant for drag, or an error while doing tracker. So what does it mean? Well, does the bottom of the slinky stay in place? Yeah, it does. Based off the model and based off the observed system, it only falls once the top of the slinky has reached the bottom end, and then they fall together. And so were all the forces accounted for? Well, we define our system to be the earth and the slinky, which includes drag, gravity, and the tension force of the slinky. If they were all accounted for, then the model should have been more closely aligned, but they didn't. So this could be due to error, or this could be due to lack of accounting for the initial force of the professor's hand, which might have altered the ability for the slinky to fall in time. Thank you.